So sorry about forcing you all out there. You can come back by me. I don't mind turning my head, but I'm a little bit under the weather, so I want to conserve all my energy. Thank you for your interest. I'm Charlie Keller. I'm one of the Meadow Rovers, and my short bio is out of the last 10 years, about 7 or 8 of them I was teaching geology at Bellevue College. So I do have a geology degree and interested in it, although previous career wasn't really geology. So I want to start the talk first by recognizing these are the lands that people have been on for thousands of years. And they've been here living with the mountain, so hopefully my talk honors those peoples, since they really have so much still to teach us about our world and ourselves. Paying homage to those. So I'm going to skip through this one real quick because this was intended to be a campground talk that I developed on some post-it notes 4 weeks ago, we did give it down at the White River one time, so unfortunately this is in development. So I was going to go over sort of what we do is in the park. Of course, you all know preservation, so I'm going to skip that. I am going to talk a little bit about the PSAR we do. I don't need to explain it to you, but basically that's for us to help visitors stay healthy and enjoy the park. For me, the essentials aren't really the 10 that the Boy Scouts have taught for years, etc. First off, the first essential is oxygen, so everybody take a breath. And I do that because I use oxygen in this talk. Most important thing, right? So if you ever have trouble, first thing you got to do is take a breath. And then also, we get that free, so you don't need to worry about that hiking. What we don't get free out on the trails are water, number 2 essential. Can't live 3 days without it. More importantly, you get up here in the mountains and you lose water faster than you do anywhere else, and you start to feel it. So if you want to be healthy and feeling great up here, drink plenty of water. If you don't, you could be in the situation where you're being rescued from not enough water. And then the last real essential in life is food. You can live 3 weeks without it. Of course, you don't need to carry much food here. I would recommend, particularly to families, have those snacks because, again, a little bit of low sugar makes your day less enjoyable. So if you want to enjoy the mountains, those. Shelter is also a list on the essentials list. Of course, that's going to protect you from rain, wind, and cold. Up here in the mountains, clothing is going to do a lot of that. Take that extra jacket because these mountains can turn from 85 to 40 real quick. And then sweaters, sunglasses, etc. for that coolness. But a hat, sunglasses, and if you're going to have skin exposed, sunscreen. Again, keep you healthy, because a little bit of sun exposure can make you feel bad, even though you don't get a bad sunburn. You're not going to have as much enjoyment up here. And then parents, remind you might want to take some extra bandages and some extra M&Ms to inspire moving down the trail. As I said, part of it is preservation. I'm going to skip that for you all and get right into the geology. So first thing I want to talk about is back to that oxygen. How much oxygen here? Does anybody know how much is in our air? About 20%, 80% nitrogen, so it's about 1 to 4, mostly nitrogen. That's good, because if it was all oxygen, we'd probably all spontaneously combust. So we need that nitrogen to dilute it. Now we need 20% oxygen to breathe. Where is that coming from? Well, all around us, and actually more importantly out in the ocean, very small little microorganisms, photosynthesis. They're breaking down carbon dioxide and water. An old story many of you probably know. They give off oxygen when they do that. And so life started, Earth didn't have oxygen at the surface. Lots of oxygen, which we're going to talk about, but not the surface, because oxygen, when it's just O2 that we need, is very reactive. So it reacts, and of course all of us metabolic organisms are using it up. Fortunately, the photosynthetic ones are breaking it. Now, are creating it. Now, that's a quick chemistry lesson is oxygen with one carbon, two oxygens with one carbon, carbon dioxide, right? You exhale it, it's very, very stable that way. So the plants have to use the sunlight to break those, and they have to use the sunlight to break the bonds of the water, H2O, to allow them to make the hydrocarbons. All that so that we can breathe and eat. Okay, real quickly, some more science lessons. Liquid-solid transition, right? Most things, when they cool, they contract. When they go from liquid to solid, they contract. Water's the exception. It goes the other way, right? Who's put a bottle of water or a can of something in the freezer? It expands or explodes if the right stuff. That's because water is the one thing that expands when it freezes. And that's going to be really important up in these mountains, because that's how we get rocks coming out of the mountains. The water seeps down in during rain or meltwater, seeps down in the cracks, gets cold, maybe daily, right? It expands, keeps pushing those cracks apart. Finally, the cracks fall off, and where do they go? They start downhill. That's the next big thing that goes through this whole discussion is gravity. This whole geology process is working by gravity. So the rocks break off, fall, and start moving down. As they do, the water starts banging them off each other. So hopefully all of you have already done it, but you get up onto the moraine trail, or even right down the White River campground, get up on the hill just above the White River, or if you really want to hear it, go down to the river itself, and you'll hear the rocks in the river banging against each other. These are boulders as big as your head, and you'll hear them banging against each other. What they're doing is rounding off. Little pieces break off, the big boulder keeps rolling down, because what's gravity doing to all those boulders? Carrying them to the ocean. Now they only get to Tacoma probably in our lifetimes, but or less or more. But all right, so that flow is going to go through this as well, because we're going to talk about multiple flows in the geology of Mount Rainier. You know, I didn't practice this, so I have no idea. Where are we on? How long have I been talking? And what do we have left? Nope. Okay. I better move quicker since you all want to get through it. Okay. So flow, I want to bring in another scientific concept. Who likes honey? Come on, right? Put a little honey out, it just stays in a mound, right? Put the same amount of water out, what happens? Flows away. And the honey maintains a slope, actually. The water flows away. Well, that's a term known as viscosity. Water has a very low viscosity. It flows very easily. Honey, higher viscosity, doesn't flow very easily. So we're going to come back to viscosity in a minute, but it's going to lead to steepness of slopes that we look at, steepness of things that we're going to see. Okay, so we talked about the boulders banging. So what are they creating? Sand and clay breaking off the boulders. So out there in the river, there is some, and you'll see it around here, some sand and clay, and it's building up on the mountain. Also, what we're going to get out of these kind of volcanoes is ash sometimes coming out, falling down. So we have layers of ash and lava and flows, and we're going to talk about those in more detail. Okay, so a lot of little details there that I'll skip because none of you are 13. Okay, let's briefly talk about the Emmons and we'll come back to it. But what do we have up on top of these volcanoes? Glaciers, right? Big pieces of ice. Now, those things are, again, flowing down. And in fact, if any of you are interested, the park did years ago, I haven't looked at it for years, I used to watch it all the time, have a time lapse from Camp Sherman. Has anyone seen it? Of the Emmons coming down, and you can see, you know, it opens up more and more during the year, and you can see the glacier flowing down the mountain. It's flowing very slowly from weight. It also melts down under the bottom and out the bottom end, so it's flowing out. So what we have, though, is a volcano that could have hydrothermal, or does have hydrothermal activity, which means carbon dioxide and water, just like you exhaled, but a lot hotter than you exhaled, it's coming up out of the volcano. It's moving through those rocks. And that steam and carbon dioxide breaks those rocks apart. So we have a mountain that's actually being broken apart as we sit here by still water and carbon dioxide coming out of the magma up through the mountain. So what are they going to do? They're eventually going to compromise part of the mountain. If we have enough pressure building below, and if we have enough of it come out at one time, maybe just a hydrothermal event, or maybe some lava breaks out and melts a bunch of the glacier along with all that hydrothermal, we get a fast melting. Those kind of events, fast melting, turn all that stuff that turned into sand and clay into mush, into mud. Pretty viscous compared to the water, very low viscous compared to maybe even the honey. And suddenly we have a bunch of mud and a bunch of hot mud, actually, now all loose, ready to flow on a 30-some degree slope. It's coming down. It's coming fast. The lahar that I'm sure you've read about and heard about, right? 30-plus miles an hour. Now, that'll be fine if you're in Enumclaw and the Geological Survey, the state of Washington, Pierce County, all of our monitoring systems that we put into place, all of our plans and preparation, i.e. the evacuation plans that they have in those valleys, allow those people enough time, we'll know it's coming, get up out of the valley high enough, because we did have a mud flow 5,600 years ago, came out of this side, went down through here, created a bunch of the deposits that we'll talk about, but that mud made it to Auburn and Tacoma, covered parts of Enumclaw and Puyallup. So it would be, and those lahars are clearly the most dangerous. 250,000 people killed in Colombia years ago when the lahar came out of the mountain. They had no idea it was coming, and suddenly they're covered in mud. Now Colombia has learned, hey, we can do the same thing. We can monitor and plan and prepare for these lahars. Okay, so that glacier's moving downhill. What's it doing? Pushing rock out in front of it and up to the sides. So the geology of our Emmons Glacier that you can read about up here, keep thinking I'm at the campground, you can read about is the moraines. Out at the end, you'll see, if you get up to the view up here, look out, you'll see the wall that's the meltwater and the braided streams running down from that. And then you see the lake down there. And just beyond the lake, you'll see a lobe that looks like a toe. And it's a mound of gravel and boulders that the glaciers pushed down there into a terminal moraine. And the glacier kept getting down that far, pushing 100 years ago. Because the maps 100 years ago show the glacier all the way down, covering the pond that's down there now, and having its terminus, its end, out at that glacier. And then as you look up or go up the moraine trail, the sides, on the north side at least, is all that rock that the glacier had been put in, sand and gravel. The glacier had been pushing up for years as it continued to push down this far. In the last 100 years, it's receded all the way back to where it is, and suspicion is it's going to recede farther. But that's our moraine discussion. But let's get into the volcanoes, because that's what the kids are most interested in here. Again, we bring back oxygen. How much oxygen in this rock? Does anyone have a clue? No. This, by atoms, half of these atoms are oxygen in these rocks. So that's the big thing that we teach, is that oxygen makes up most of these rocks. So it's down there, it mixes with iron and silicon, and the iron makes it crystallize soon at high temperatures. So when it does that, it forms the beginning of the rock that many of you have heard out, basalt. And those are the kind of rocks that we're going to find. That's the kind of magma and then lava that flows out at Hawaii on the Big Island. So it's been flowing there about 500,000 years as that island built up. Oahu, if you've been to that island, is about 2 million years old. And the islands further north, 3 and 4 million years old, because they're all formed by a hot spot that has moved under and created each of those subsequent islands. So there now is a current one forming off of the Big Island of Hawaii to the southeast. That's because that is low viscous lava. So it flows like a river. If you've seen pictures of those flows, they break out and they flow away to the river. There's nothing spouting usually, or it's very small. And usually not any ash. Maybe some steam is about all you see coming out of it. But we can get a situation where the ground, where the magma underneath changes chemically and the iron starts coming out of it. But without the iron and with the other metals that are now in it, it becomes far more viscous. So then we get to the next type of volcano, from the shield, the Hawaiian volcano, which looks like Captain America's shield, to the cone, hence Mount Rainier. Yeah, I did want to go back, because there was one point I wanted to make about that commonly basaltic lava, and then we'll talk about it here, is that as it flows out, it starts cooling from top down, right? Because the heat's coming out the top, so the top starts shrinking. And as it shrinks down, it starts shrinking into little somewhat circular patterns, but they take on a hexagonal shape. So the hexagonal columns that you see in eastern Washington are from the fact that those layers and layers of basalt that flowed out 15 to 30 million years ago, the layer would flow out, it would start cooling. It takes a long time to cool. Those things don't cool fast. And so they would create those cracks that run straight down, but you look at them from the top and they have that hexagonal pattern. So that's what creates the hexagonal pattern you'll see in the Columbia River Gorge.
Also on Mount Peak in Inuqua has a couple sections of them.
Yep, we're going to talk about our columnar andesite here. But the hot spot that created those Washington volcanoes, we've moved, so it's now passed across Idaho and in Yellowstone now. And so that's what creates the hot, which creates all the Yellowstone hydrothermal activity and potentially a very large volcano, but not in our lifetime. Okay, so what happens when the iron gets out of it? Then we form the andesite, named for the Andes Mountains. So the Andes Mountains are just like the Cascades, a chain on a continent next to a subduction zone. So we won't get much into a subduction zone other than that allows the chemistry to change. So we don't have so much basaltic, low viscous lava. We have higher viscous andesite. So when it flows out, it doesn't flow very far because it flows down to where it's a 30-degree slope and then it stops. So one of the things I want to try someday is setting up kids to color at a campground top. But the magma at the Hawaiian Islands goes like this because it's low viscous and flows away. The magma here starts to build up in layers that have that 30-degree slope. So that's the difference in the shield and the cone volcanoes. High, more viscous lava, so it doesn't flow as far away and starts building up that 30-degree slope or higher. Okay, so we talked about the continental arc. So we have in a continental arc along a subduction zone, which is the Pacific coast, effectively from Canada all the way down to past Peru and Chile. And so the Andes are just like the Cascades, where that creates a hot spot that is a certain distance, depending on how steep the subduction's going, a certain distance. So in Peru, they're closer to the subduction zone, closer to the coast, than we are here in the Cascades, because it's dipping down at a steeper angle. The subduction's going in. So that's it. Subduction is one that's always hard to talk about, but because it is such a huge concept to imagine part of the crust going down in under other crust. So what happens then with this andesitic type volcano? Well, they start being viscous and they can plug up in the vents. So sometime that vent can plug up, a bunch of pressure can get built up, and it can blow out the top. Or if that hydrothermal activity broke down the side of the mountain enough, we can get a landslide that slides off the mountain. That's what happened at Mount St. Helens. We kept seeing the bulge because the north side of the mountain had those cracks that all that hydrothermal stuff was coming up through, weakening and weakening and weakening. And finally that whole thing with one volcano or one earthquake broke and fell away. Now some of you might have heard of the swarm of earthquakes that we were having in the area months ago on Mount Rainier. Nothing close to the swarm that occurred on Mount St. Helens, which started in early March. Through April and into early May, it was clear something was going to happen there because the earthquakes were just rumbling all the time. It wasn't a question for the USGS in Vancouver, Washington's office to see whether we were going to an earthquake on Mount Rainier today. It was how many, how deep, and how big they were going to be because they were all day long regularly then. So luckily, they got to the governor, and being a scientist, she knew, hey, these people know what they're talking about, and so she closed the area down. Evacuated the area, saved well over 500 people, because Spirit Lake was a common vacation spot. Middle of May, all those owners would have been coming out of Seattle for their, or Tacoma for their vacation spots, and it would have been full. I've talked to people whose families had places on the lakes and said, oh, we would have been there. And in fact, they knew people who said, we're still going. That was a fatal mistake. What happened? The side collapsed. It blew out the side in a pyroclastic flow. So this is when, because we relieved all the side pressure, what's coming off the side is vapor rock. Yeah, gaseous rock. It's this rock that would be crystal if it wasn't thousands of degrees. And so when it came out in a blast, it's traveling at probably 200 miles an hour, or at least 100 miles an hour. And just, if you've been there, the trees are knocked over from that blast, and they're scoured clean because they got hit with either molten sand or sand that was partly molten. And of course, unfortunately, the USGS scientist watching was able to say, it's happening. And that's the last word and last example of, or last evidence of him, because that blast vaporizes immediately. All right, so let's do the quick geology tour of the area, and then you all can get to eat. We're going to go back 30 million years ago. Of course, we had basalt flowing out of the ground through huge ruptures in eastern Washington, covering vast areas, basically half of the state. We come forward, and about 14 million years ago, we had some of that lava, some of that magma, which has changed composition now, and doesn't have all that iron in it, so it's not basalt. It's even gone further than the andesite, and it's moving up and stopping because there wasn't enough pressure. 2, it's not as hot anymore. 3, it's far more viscous, so it can't force its way up anymore. It stops, cools, forms big crystals. So as you come in the park, or come in the White River entrance, and all the way down and through towards the White River campground, you'll see the rock that's left over from that rock that cooled underground, the granodiorite. Big crystals because it cooled way underground. Within 14 million years, it got scraped off and eroded off enough that then when 500 million years ago, this volcano started to grow and that andesite started to flow out of it, it got covered up, But now we have places that it's been eaten away. So we see that granodiorite formed way at depth, miles at depth, now at the surface. And now we can use it for rock walls at the sunrise lookout, picnic table walls, visitor center walls, or picnic table stands of that granodiorite formed 14 million years ago at depth. Come forward 500,000 years ago, 500,000 years ago, this andesite starts flowing here and starts building up this cone. About the same time that the Hawaiian Islands started flowing. You can see though, we have a little 20-mile wide cone. They have a 120-mile wide shield. Okay, then as we come up, the last two geology things, as you come along the White River and then coming up at times, you'll see places where it's all crumbly stuff on the side of the cut. It's all crumbly. There's big rocks in it. There's little rocks. There's sand. If you went and tried to climb it, it'll crumble down. That's the mud flow from that 5,600 year ago Ocello mud flow that left deposits all around us down in the White River. As you come up the road then, we come by about halfway up, I guess, you'll see the columnar andesite now, not the basalt from eastern Washington, the columnar andesite popping out. Now, unlike eastern Washington where they're vertical, as they cool up, we believe that andesite flowed in, stopped, right, because it got shallow enough depth that it's not going to flow anymore, some 20 degrees or so. And there was a glacier still here. Well, that andesite's going to cool over a long period of time. If there's a glacier coming down the side of it, that cooling now can get directed out the side of the glacier, out the side of the andesite flow, sit up the top, so we get that same shrinking in the columns that form the andesite columnar jointing we have there. Now, if this was a campground talk, I'd remind everybody there's a couple pullouts there. You can stop and look at it from that side of the road. Don't cross the other side of the road and try to get too close to it because there's nowhere to walk and it's an active road and you're going to get hurt. So stay on the opposite side of the road to look at our columnar andesite, please. Okay, then we're now, nope, did that page too early, the Emmons Glacier and the moraines. So that's effectively the quick round of my geology for Mount Rainier. Thank you. Any questions? Where did you say the?
So in Enumclaw, Mount
Enumclaw.
Peak. So
Okay.
that's andesite.
I don't know. I'm
No,
going to have to look that up.
they're
That could be
horizontal.
basalt too.
They're horizontal.
They were horizontal?
Yeah, they're horizontal.
Yeah, that's andesite that probably, and most people don't, in fact, in geology school classes, we don't teach about columnar andesite because it's common in basalt. It's not so common in andesite. So, but it's here. Mount Baker has some really nice deposits of it there.
We have some pretty spectacular examples.
Columnar andesite, the columnar jointing in andesite.
South Puyallup Camp just is stunning.
Pardon?
Have you been out to South Puyallup Camp
No.
on the west side of the mountain? They have some stunning columnar andesite.
Oh, really?
They're best in the park, probably.
Cool.
Okay.
Thank you, Charlie.
Oh, you're welcome. Hope my rushed partial version, because I'm still, I'll let you turn that on.